when we sketched functions before, like trig functions or even polynomial functions, we reflected on why we do it a little bit, but it's always a good idea to come back to that. And, the functions that we look at have some pretty, like, some of the properties are very similar. For example, intercepts are always kind of one of the things that we look at, right? Polynomial functions, that was a big part, is the X-Intercepts, and then we would always find the Y-Intercept as well. And less so in some ways with trig functions, although sometimes the intercepts are important, but we don't necessarily graph with them. But anyway, but it really helps us understand what the function's doing. Learning how to sketch means you have to know what is important about the function. Like, what makes an exponential function different from a rational function or different from a polynomial function or whatever, right? Like, you gotta know the defining characteristics of the function. That's really what it's about. And then we do the algebra to learn how to calculate some of them, at least. I think algebra just on its own, if you've thought about it, it helps us manipulate expressions, and so it's just a skill that we can do that kind of thing. But otherwise it doesn't have any meaning. But then when we start looking at graphs or sketches of things, we understand what impact algebra can have. And I don't mean like factoring, because that doesn't change a function, but I mean like, changing the a value or whatever it is, how that changes things. So so then in real life, like, how does that change the growth of a situation, right? It all does boil down to modeling something in the real world. That's the whole point of math, is eventually, right? So while you're sketching over the next few days, keep that in mind. Like, I think it can help to think about why you're sketching. And then very specifically, if you have like a target, in order to sketch, I need these important characteristics. So I'm going to calculate them first and use them to then define my graph. And when we started, grade 9, a little bit with the slope and the Y-intercept, that's true. You find the Y-intercept, and then the slope tells you where to go from there, right? So the two characteristics, that allows you to graph. But then it's a little bit more interesting when you get into parabolas. We do the same thing. You're trying to find the vertex, and then you're trying to find where the other points are. And we have different skills for doing that. And that's how we graph. So it's the same thing for rational functions, just even more so than, I would say, trig functions and polynomial functions. Rational functions kind of have more going on, more possibilities, different kinds of things we have to figure out. So that's what we've been working on for a few days. So here you go. Whenever you sketch a rational function, these are the 3 things that you have to do. And you have to show the work for it. We're going to organize our solution in a particular way, just to make it clear, because otherwise it could end up being a lot of kind of messy scribbling all over. But we're going to do these 3 main things. We're going to find all of the intercepts. You have to, and then we're going to mark them on the graph when we sketch. We have to find the asymptotes. That's pretty important for rational functions. And then we're also going to find the behavior around the asymptotes. And that is how I know the difference between a graph I have, if these are the asymptotes. How do I know? Thank you. How do I know that the graph looks like this, or does this, or there's lots of other kinds of things it can do, but how do I know which one of those graphs it is? Because I had this conversation with a couple of people the other day, or over the last couple of days. You can't really tell just by looking at the equations. Like, even I can't really tell. I've looked at it a little bit, but it would take a lot of work. Thank you. It came out. Thank you. Yeah. But it's not obvious, and it's like it's harder basically. It's easier, even though testing behavior around asymptotes is a bit messy. It's the better way. So that's what we're going to do. Okay, but like if you're looking for the steps, step 1, step 2, step 3 kind of thing. Okay, and you gather all that material, and then with all that material, you make your sketch. So let's give it a try. And I think it's important that you come up with a structure for your solution and even sort of an order and just do it the same way every time. That often makes it a lot easier. Okay? And like I said, it can be, we do a lot of tiny little steps, little 2-step things. And so if you're not clear about what it is, it's not going to be obvious for somebody. And you know, some of us are very good at organizing our writing so it's clear when something ends and when something new begins, but a lot of us are not as good at that. And so we're going to use little titles and that kind of thing to organize our stuff along the way. So we're going to start with the intercepts. Okay, and in this case, we're going to start with the Y-intercept. And the Y-intercept is quite straightforward. It always is. It's one of those things that it's the same in every kind of function. Functions are designed where you put in the input and you get the output. And so we can put in a 0 and just see what we get out, right? So it's super easy. So that's what we're going to do. We just sub-0 in, and you should always show the substitution step. But you don't have to show any other work. And we're going to graph. So 3 over 4 is a straightforward fraction. But in general, decimals are easier to graph with, right? So we're going to write the decimal as a general habit because that's what's going to help us graph. Now we're not accurately graphing, we're sketching, so we're just going to mark points. But it will be important if that point ends up being above or below an asymptote. Like it may or may not work out to be close, but that's something to think about. And you know, approximately how high it is, that is something that we should think about. So you want to know the decimal value. Everybody okay with that? Finding the X-intercepts is a little bit more involved, usually. To find the X-intercepts, what do? We sub-0 in for Y. So I end up with 0 equals the function. I think we've kind of talked about this already, where the denominator of the function is not going to be relevant because like nothing in the denominator will make the result be 0, right? Nothing in the denominator is going to make my result be 0. So we'll only care about the numerator. So in this case, when the numerator is 0 is when we have an X-intercept. That's what's going to make the whole right side 0. So when 2x squared minus 3 is 0. So how are we going to solve this? I'm going to just solve it by isolation. In some cases, you might factor. Be using the bottom? When the bottom is 0, gives us what? What does it give us? Oh, I see what you're getting at, but gives us an asymptote. If the bottom is 0, we have an asymptote because you can't divide by 0. There's always a reason behind it. So if you start getting yourself confused, think about the reasons. There's always a reason behind it. When you divide by 0, that's not possible. You don't get an answer. That's what an asymptote is. When the top is 0, the fraction is 0, which is what we want. We want y to be 0, so we want the top to be 0. Now, but you said something really important there. What if we had a common factor in the bottom? Then it would be a whole. It wouldn't be an X-intercept. We don't need to worry about that yet. That'll come out in the wash. So that's something we'll need to consider eventually, but we're not going to worry about it yet. So I've got x is plus or minus 3 over 2, 1.5. So again, I'm going to do on my calculator, punch in the value. So go ahead and do that. And we've got 2. In this case, it's absolutely important that we have 2. I got 1.22. And that's it. We've got our intercepts. Okay with that? Yes? No? How we feel? Most of the work and skills there's nothing really new. We've been doing that. We're experts at factor. If we had to factor the top, we're experts at that. We're good at solving little quadratics like that. Or even there's going to be cubics. Like there's going to be slightly more involved ones. So don't be surprised by that. If you've got a cubic on top, well, we just finished a unit solving polynomial equations. So that's fair game, and that's part of what we do. Whoops. Now we're going to do the asymptotes. And the behavior around the asymptotes. I don't know why, but we're going to start with the vertical asymptotes. Again, it's nice to have a structure, like do it the same way every time. It'll help you, I think. So we're going to start with the vertical asymptotes, test the behavior, and then go to horizontal asymptotes, test that behavior. Okay. When we do the vertical asymptotes, this is what we just talked about. What has to happen to the function? What gives us a vertical asymptote? The bottom is 0. So go back up here. When is this going to be 0? Well, that's a grade 10 question. And we solve it the same grade 10 way by factoring it and looking at what the factors are. So that's the first thing we're going to do. Is factor it. Go ahead and factor it. Okay? So my vertical asymptotes are x equals 4, positive 4 over 3, and x equals negative 1. And 4 over 3, again, that's helpful to have that as a decimal. That's approximately 1.333. Actually, for another reason, I'm going to write down a few more 3s. Okay, and so let's start with that one. Now we're testing the behavior around the asymptotes. This is what we were doing yesterday. Testing behavior on asymptotes, as I said, is messy business. But I said it's worthwhile to think about for a few reasons, because it helps us really understand asymptotic behavior. But it'll also help you like pick which values. And I mean, I try to imagine what students are thinking as I teach, right? Like, because especially if you don't get a lot of feedback, you don't get a lot of questions or whatever, I can only try to assume what's going through your minds the first time you're ever seeing this. And one of the things I can imagine is it seems simple. Picking a number that's bigger or smaller than the number we're looking at. People take it for granted, but then when I mark learning goals or quizzes or tests, people do it wrong. People pick numbers that are smaller when they're trying to. Because of a negative or a decimal or something like that. And part of that is just like, maybe we take it for granted, we think it's easy, and so we don't spend the time really like, oh yeah, right, I got to do this. Like I got to think about what number decimal place value they call that, right? I don't know exactly what it is, but it's something. But to make you aware, keep that in mind, that people do make mistakes picking numbers that are bigger or smaller. And part of that is they don't really think about like why they're doing what they're doing or what exactly it means. So try to think about that. If you didn't yesterday, or if you haven't yet, maybe this weekend, or maybe tonight as you're doing some of this work, really think about exactly what's going on here. So we're going to do a couple of things. Don't write this part down, just watch. If I pick f at 1.33, some people will pick 1.32, and that would be fine. That's not wrong, that'd be fine. This is kind of a side note, by the way. But 1.33 is less than 4/3, right? Because if it has more threes, that's going to make it bigger. Like that's rounded down. That's 1.330. That's rounded down from 1.333. See what I mean? Because it's repeated. So if you ever get a repeating one, you can just truncate as a way of using a smaller number. This one gives me negative 23. Don't write this down, 0.05. And I don't think that's big enough. I want a really, really big negative number. I mean, it's kind of going to be okay. So this is a vertical asymptote. I'm picking a number that's a little bit, from your perspective, a little bit smaller. So a little bit to the left. And it's gone really negative. But I just want a slightly bigger number. So I'm going to go with 1.333. And then I get, what do I get? So I'll plug this in on the top, 2 times 1.333 squared minus 3 divided by, and you're going to notice that in some cases it's easier to use the factored form, in some cases it's easier to use the other one. And so that's going to be part of it. In this case, because of the coefficients, it's kind of messy. So I don't know. It's your call which one you think is better. Anyway, 3 times 1.333 minus 4 bracket 3 times, 1.333 plus 1. Oh, shoot. I got an error. I got 2 times symbols. There we go. That's nice. Negative 237, not that it matters, 0.4. Really, all that I care about is that it's negative. So you're going to see that actually sometimes we're not even going to find that value. We're just going to see that it's negative. Because of the way this question is, I decided to punch it into my calculator. You may not always have to. What's going to be a value that's slightly bigger? 1.334. So I've looked at this one vertical asymptote. Like, picture what these graphs look like. Do I have it here somewhere? Where is it? There we go. when I have an asymptote, maybe they approach both going down, approaching from the left and the right. Maybe from the left it's going up, and maybe from the right it's going down. This is what we're trying to determine. So we've done that for one asymptote. This one works out to positive 119.8. Again, that doesn't matter, but it's positive. That's what's important. Is that okay? I'm going to make my, and you have to do a conclusion statement for each of these as well. So here we go. As X approaches 4/3 from the left, Y approaches negative infinity. As X approaches 4/3 from the right, Y is going to positive infinity. Are we okay? Okay, that was one of our asymptotes. The other one is X equals -1. And again, in my head, I always try to start from the left and then do from the right. It doesn't matter. But you need to know what you're doing. And I do think it's important that you think about it with some purpose, especially when you get into fractions and negatives and that sort of thing. Is you have to think about what would be from the left when it's negative and it's a fraction. What would be a decimal value that's from the left? Because I can't use 4/3 and use 1 and 2. Like you can't, that's not close enough. It's nowhere near close enough. We're getting within 0.001 decimal place of the number. That's how close we're getting. Because an asymptote gets very close. That's how close we want to be. Right? So you can't cheat and use like 0.5 or something like that. It's too far away. So just to the left of -1 would be a number that's a little bit bigger negative. That would be further to the left on the number line. It's closer to -2. Between -1 and -2 is to the left, so that's smaller. And this works out to a very large negative number. And so then as X approaches -1 from the left, and that's why, because you need to know, is it approaching from the left or from the right when you write your concluding statement and then when we go and sketch. So this one's going to negative infinity, and then F at -0.999 is positive, is a large positive number. On my calculator, I've already done it, so that's why it seemed fast, but I did that part on my calculator. As I said, if you could do it in your head, often you can. We'll see that in the next example. Then do it, because we don't need the value. For vertical asymptotes, when I'm really close, let's go back and look at this again. When you're really close, you're really far positive or really far negative for a vertical asymptote. So that's the behavior we're looking for. That's what the values we're expecting to get. Okay? I've done both vertical asymptotes from the left and from the right, and then the other one from the left and from the right. There were two, so I've done both. We only showed one value for each. That's all you have to do yesterday. I know we did more as a demonstration, but you don't always have to do more. Make sure I have enough room here to sketch when I need to. Now I'm going to come up and do the, so those are vertical asymptotes. Now I'm going to come up here and do, if you have enough room on your page, you could do it below there as well. I'm going to do the horizontal asymptote. Again, we have two versions of our our function, of the equation for this function. Which one do I want to use to find the vertical asymptote? Usually the expanded version. I've got x squared on top and x squared on bottom. They're both degree 2, same degree. All that thinking is important. So it's just the coefficient of each. We saw an example yesterday where it was like written out of order, so you got to really think about what the coefficient is. But in this case, it's just 2 over 3. Okay, so y equals 2 over 3 is the horizontal asymptote. I just want to point out here, if it was in this form, I can't just take those two numbers. Turns out that works. But if this had a coefficient, when we expanded, that would be part of the leading coefficient, right? So if this was 3x and this was 2x, my leading coefficient in expanded form would be 6. So when it's in factored form, I got to think about it a little bit more. You could still do it, but if you have expanded form, you could just use that, but it's up to you. But that's part of, again, that's part of what I said, like having to sketch means we really have to think about all these little details about the algebra and what it tells us and how it relates to the properties and all kinds of good thinking. Everybody okay? So now I'm going to test from below and from above. So from below, I'm going to use a really big negative number because, again, if I go back and look at what it's like, sorry, I don't know which one I'm doing, if it's below or above. That's part of what we're checking. But I'm going to test the left side of the graph first. But as this shows, it might be above. And then I'm going to test the right side of the graph. Again, just a specific order to help me kind of keep my thinking structured. And in this case, we have to do the math because we have to get the answer and see if it's above or below. It doesn't matter if it's positive or negative. Both of these are positive. So I have to do the math, right? We have to, for the other one, you may not need to actually use your calculator. In this case, we do. And because of the way this function is, it's kind of messy, so you really have to use your calculator. Okay, so go ahead and punch that in. The one part you might be able to do, well, 2 times negative 1,000 squared minus 3. If you can do that in your head, go for it. And we're going to do the other one. So a big positive number. And I get 0.6669. I think, did anybody get the same thing? 6664 and 6669? Interesting. Yeah, I think it's 4, and there's a reason for that. So just check if you missed. The only difference between the two when you punch them into your calculator is one little negative sign in the denominator. It's the only actual difference. Because when you square negative, square positive, you get the same thing. So it really ends up like, if I use this version, it really ends up right here whether I'm adding or subtracting that. So it might have just been a small little mistake like that. So when I look at these two, which one's above, which one's below? Or are they both above, or are they both below? And this one's slightly below. And you look at how they do approach the asymptote, right? It makes sense. That fits. And this one is slightly above. So that means as x goes to negative infinity, y is approaching 2/3 from below. And as x approaches positive infinity, y is approaching 2/3 from above. I've got all my concluding statements. I've got my intercepts. Got basically everything I need. Now I can sketch. If you want to watch, that's for a minute, that might be fine to kind of see the order of my thinking and how I sort of approach things. If you can follow along and do it at the same time, that's okay too, obviously. So I'm going to draw in my two asymptotes. And it's not an accurate graph, it's scale. It's a sketch, sorry. So it doesn't have to be to scale, but you should take some consideration into where approximately your asymptotes are relative to each other. So this is -1, and my other is positive 1.3, so it should be a little bit further out, kind of thing. Where are my x-intercepts? Plus and minus. Oh, and then I'm going to do my y-asymptote, so 2/3. Sorry, my horizontal asymptote. My y-intercept is 0.75, so that's a little bit higher. My x-intercepts are 1.22, so that's inside the 1.3 right around here. So that's positive 1.22. And this one's going to be outside negative 1.22. And all of this should match, right? There's a couple of different kinds of graphs where the x-intercept and the asymptotic behavior tell us something really important. And to some extent, two behaviors around asymptotes can do the same thing. So we really are putting all these different pieces to the puzzle together. So from here, where you start is kind of up to you. This is the part where you might want to just watch. What does this tell me? As x approaches 4/3 from the left, y goes to negative infinity. So that tells me that this part of the graph is going to be down here. As I'm approaching from the left, I'm going down. You could do tiny marks with your pencil or something like that. Okay. As x approaches 4/3 from the right, y goes to positive infinity. So this one goes up there like that. My other horizontal or vertical asymptote, as x approaches -1 from the left, y goes to negative infinity. So that one's going down on that side as well. And as x approaches -1 from the right, y goes to positive infinity. So that one goes up there. So, and that makes sense with my x-intercepts. I'm just going to get rid of that one so it's out of my way. And this one's going to go like this. See how the puzzle came together it goes through the Y-intercept, through the X-intercept. It's going down to that asymptote down there. It's going up to that. Like, it has to fit all those parts. And it should be a clear picture in your head after you've put all those pieces together what that part of that curve looks like. That's how you find out what it is. And then lastly, my horizontal asymptote here. As x goes to positive infinity, I'm approaching from above. I might want to make a note to myself about that, from above. And this means from below. And I already figured this one out, so this one just goes like this. And then as x goes to negative infinity, it approaches from below. So again, that makes sense because I'm coming from here. I'm going through that x-intercept. And there's my graph. I'm gonna label my asymptotes because there's no scale and it's a sketch. We have to label our values. So this is x equals -1. This is x equals 4/3. And this is y equals 2/3. And I've already labeled my intercept, so I'm good. I'm going to dive right into the next one if everybody's okay, because I want to do one more and we're kind of running out of time. I hope we can have time to finish it. Good? Questions? It's a lot of work for one. I think I said this yesterday. They're worth like 12 marks or something like that on a test. But a lot of them are easy little things, right? Like, punching some numbers into your calculator. Once it clicks, you get the hang of it. It's not too bad. But it's a long process, takes a long time, there's a lot to do. That's why steps help. Okay, so what do we start with? Intercepts. Y-intercept. Plug 0 in, so 0 plus 2 over 0 squared plus 7 times 0 plus 12 is 2/12, which is 1/6, which is about 1.167, not that that matters, but, or 1.17. And the x-intercept is just, not equal. 0 equals x plus 2, so x is -2. Asymptotes. We often start, I got to factor this first. Because we need to know where the bottom is 0, and we do that by factoring, and this one's pretty easy, x plus 3, x plus 4. So the vertical asymptotes are x equals -3 and x equals -4. So let's start with x equals -4. We'll work from left to right. Doesn't matter. Pick one. You just gotta be thinking and aware of which one you're doing and what you're doing. Okay, so I'm going to explain this a little bit more carefully. I'm not going to fly through this part because here's where, so if I'm doing -4 from the left, what would be a good value to use? Yep. Nice. And here's where you can just look at factored form and figure out if it's negative or positive, right? Because -4.001 plus 2 is going to be negative. -4.001 plus 3 is still going to be negative. And -4.001 plus 4 is going to still be negative because it's a little bit bigger. You're not quite adding enough to make it not negative. So that's going to work out to negative. So see how I just quickly do it. I don't need to show, you don't need to show the value, but you need to just state whether it's positive or negative. This is the kind where all the coefficients are 1. You might be able to do it in your head. I would encourage you to do so. Saves you a bit of time. And then what would be another one? 3.999. 3.99 would work as well. Like that's gonna give you the same value. So you don't have to use 3 decimal places. You could use 2 here. But it won't make a difference, especially doing it in your head. So negative 3.99 plus 2 is negative. Negative 3.99 plus 3 is negative. But negative 3.999 plus 4 is positive because 4, the positive value is a bit bigger. I've got 2 negatives. That makes a positive. Write our conclusions. So as x approaches negative 4 from the left, y goes to negative infinity. As x approaches negative 4 from the right, y goes to positive infinity. It's not always opposite. People try to come up with their own rules. If one's positive, the other's negative. No, we've seen examples where from both sides it goes to negative. So it doesn't always happen that they're opposites. This is the problem, is there aren't patterns like that. There's too many different kinds of examples. Whoops, so now I'm doing x equals negative 3, the asymptote. So I'm going to pick a value just to the left of negative 3 and a value just to the right of negative 3. And go back and look at that factored form. So it looks like I'm going to get negative, negative, positive. Do you agree? So 2 negatives makes the overall positive. Right? That one's going to be negative because negative 3 is bigger. Negative 3.001 is bigger, so that's going to be positive or negative. That one's going to be positive because 4 is bigger. 2 negatives makes overall positive. And then for the next one, I'm going to get 1 negative, positive, and positive. So this next one's going to work out to negative. Yes, Megan? Negative 3.001 plus 4. 4 is bigger. That's going to make it positive. Is that what you're talking about? That's a 3. X squared plus 7x plus 12. It was a nasty 3 and I tried to fix it and I think I made it worse. Okay. We got that. We make our concluding statements. As x approaches negative 3 from the left. See, so much from the left, from the right, from above, from below, from this way. That, like, I know there's so much stuff. And sometimes as x approaches a number, sometimes as x goes to infinity. This is the part that you got to get clear for yourself, right? You got to work through it to the point where you're starting to get it and you can do it consistently. So y goes to positive infinity, and as x goes to negative 3 from the right, y goes to negative infinity. We good? Okay, and then my horizontal asymptote. Does anybody know what it is? Some people might say it's 1 over 1, but it's not. It's 0. Why is it 0? Because this is like 0x squared over 1x squared. If the degree on top is lower, it's always y equals 0. You look back at the definitions. Definitions are not useful the first time you see them, but they can be useful later to look back and reread them after you've started working with it. You're like, oh yeah, now I understand why, if the degree is the same or lower on top, there is a horizontal asymptote, and if it's lower, it's always 0. Okay. Anyway, so what do I do here for horizontal asymptote? I do when f at negative 1,000 And in this case, I'm going to do this part quickly. You do it on your calculator. I get negative 0.001. Something, 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 something. And then when I do... For some of you, you might do the conclusions as you go. For some of you, you might like to do both and then write your conclusion. It might help having both answers written in front of you. This one works out to positive 0.000995. You don't need that many digits, but you could even truncate. I mean, it wouldn't be wrong, but it would round up to 1. I just decided to keep writing decimal places. So for this one, as x goes to negative infinity, because x is getting really, really big negative, y is approaching its asymptote, 0, from below. And for this one, as x goes to positive infinity, y is approaching the asymptote, 0, from above. I just want to really point out that like vertical and horizontal are quite different. What you put into test is different. Again, you got to get used to that. And what you get out is different. In this case, I'm getting out a number that's very close to the asymptote. And either just below or just above. That's what we're trying to figure out. So both of those, this is just below because it's negative. 0 is nice and easy because it's just negative or positive. This one's just above. We good? We got everything we need. We got our intercepts. We got our asymptotes and our behavior around our asymptotes. We can sketch. This one has, I'm glad I rushed a little bit. I know it's, a little bit trickier, but both of my asymptotes are on the left. They're in the negative, so I'm just going to keep my axis to the side there a little bit. Something cool happens in this one that we need to think about, so I'm glad that, I hope I'm not going too fast. So drawing your asymptotes. Negative 3 and negative 4 are our verticals. My horizontal asymptote is x equals 0. If you can, like use a different color or try to show it on your graph. That's not just for me, that's for you. It's helpful to have an asymptote to look at. I noticed in the last learning goal, some people were trying to draw lines and they didn't have an asymptote there, and then their line was quite wrong. Like they actually approached, it was supposed to be at 3 and they were going to 2, because you just can't tell on a little graph, so it helps to draw them in. My intercepts are at, I have one X-intercept at negative 2. So where's that? That's over here to the right of this. Those aren't very well drawn to scale, but we'll have to do. And my Y-intercept is 0.167 or 0.17, so it's positive, and it's not very tall. 17. All right, let's start doing our behaviors. I'll start with x equals negative 4. So as x approaches negative 4 from the left, it's going to negative infinity. So it's going down there. As x approaches negative 4 from the right, it's going to positive infinity. So it's up there. As x approaches negative 3 from the left, it's going to positive infinity again. So it's there. So it's turned somewhere. But there are no X-intercepts in between those two asymptotes. We would have found them. They would have been calculated. They can't exist if they didn't come out algebraically. So it turns somewhere. We don't know where. In calculus, you learn where. And that's one more step. If you think these sketches are hard in calculus, they're worth 20 marks. Because you got to just because you have more skills, you can calculate more things. I'm not the bad guy here, folks. I didn't do this to you. I didn't make math up. I didn't design it. I'm helping you through it. Right? So it turns somewhere. We don't know where. That's okay. Okay, keep going. I didn't do negative 3 from the right. So negative 3 from the right goes to negative infinity. So that one's going that way. But here's, okay. And then as f goes out to the left, so as x goes out to the left, goes to negative infinity, y is approaching 0 from below. Remember, that means from below. I'm going to zoom in here a little bit. So that means this one goes like this, like we would expect. Here's something that's interesting, though. As x goes to positive infinity, y approaches 0 from above. But look at how that matches our intercepts. Our y-intercept, like we're starting down here, right? But our y-intercept is above the asymptote. I'm not approaching that asymptote from below. And there's an x-intercept. All of that fits together to show me that I go like this. I cross the intercept, and I cross, and I approach from above. It doesn't cross again. There would be another x-intercept again. But I know that it goes up, it crosses. I don't know exactly where this little bump happens. I haven't drawn it to scale. This is where, especially those of us that are not good artists, it can be nice to graph it in graphing software, see how close you got. Like the solutions online are great, but graphing it accurately is even better. Some of that will look different depending on how you change your scale. Like if you drag your x-axis out, or right, that stretches the graph, makes it look different. And we don't have a scale, so we're not too worried about that. But it just could be interesting to start getting a sense of where's this little turning point? Where is that turning point? Is it up really high? And I think it is. I think it's like, I think I graphed this once and it was off the graph or something, but I don't know. Or it's at like 6 or so. It's like high, relatively high. Is that okay? I know that's a lot. Folks, do the practice. It's going to keep getting a little bit harder. Tomorrow we start oblique asymptotes with a little bit of sketching, and there's a whole added layer of work to that. So do this work tonight, which I haven't handed out yet, so I'll do right now, so that you really get as much of this stuff as you can.